Swayam Prabha. Digital India. Educated India.
Good morning. Welcome you back to this lecture in this course on analytical, spectral and microscopy applications of inorganic compounds and nanomaterials. We have been looking at the past few classes on the infrared and Raman spectroscopy, which is in general is the vibrational spectroscopy, and lately in the previous class we have started looking at a lot of applications, examples, the comparison of frequencies and so forth. And so let us we have looked at the frequency, the metal nitrogen frequency in this case of the complexes. Of course, I explained to you in the previous class the ethylene diamine complexes of all these, all are octahedral, all are ethylene diamine complexes trace. And if you compare the frequencies of manganese, iron, cobalt, nickel, copper, zinc, you will see the trend of this stretching vibrations exactly follow the trend of the Irving-Williams series of the stability metal complexes of these divalent transition metal ions. Okay. So, I have already prior to that demonstrated you how you can see the influence of the mass difference either by the metal or by the ligand. The ligand means going from X, from fluoride to chloride to bromide to iodide, or metal can be a 3D metal to 4D metal to 5D metal. So, any of these kinds of things can influence and make. Also I have demonstrated to you how the geometry, the cis versus the trans, the lesser the symmetry, that greater the number of bands or splitting is more, and the greater the symmetry is the lesser number of bands. It is very commonly found, and it is much more easily found even in the carbonyl chemistry used also. Based on the number of bands, the symmetry has been fixed as well, and therefore the corresponding structure aspects as well. So, from the infrared number of the bands, shape of the bands, size of the bands, position of the bands, intensity of the bands, you can determine the structural features, symmetry features and many things in that. Now you can understand that. So, comparative way is the best way in that. Now look at one other example here, the effect of the geometry. I have already shown you, but another example here, and effect of isotope here. So, let us come to this right side spectrum in this particular slide, and this is nothing but zinc dichloro-dipyridyl complex. Okay. So, neutral complex, zinc is zinc 2 plus, and so therefore you have all the 4 ligands in this, and the zinc will not show the square planar, you know, for the reasons, and it is tetrahedral. And so you have a spectra in the top with the infrared, which is absorption mode, and in the bottom you have the Raman spectra for the same. Now let us try to look at these each one of that, and you have 2 spectra. One is the dark line, which is a filled line, and another spectrum which is the broken line. So what do you see the difference? If you look at from distance and then say, oh, both are same. But if you look close by here, for example in this particular the region here, both the spectra are different, there is a shift. So what is the dark one, which is 64 zinc nucleus, and the broken one is the 68. So that mass number is changed by 4 numbers, because 1 by 64 in one case, other case 1 by 68 to get the reduced mass. So it affects the reduced. That is what is the effect of isotope. So effect of isotope is nothing but the effect of the mass itself, but we are explaining here through that. Earlier I explained through platinum versus palladium, chloride versus bromide, iodide, etc. Here we are explaining same metal ion, same metal nucleus, but different isotopes. So zinc with the 64, zinc with the 68. Now you look at this particular band, again the same, this particular band, again the same. So what will happen? 64 to 68, mass is higher, the frequency should be lower, and you see that this dark one is a higher frequency, is lower frequency, higher frequency, lower frequency, higher and lower, absolutely perfect. So same thing, I don't need to repeat to explain you for the Raman spectrum, also the same thing. So, the frequency moving lower for the lower isotope, the higher greater mass, that is where you get the lower. So, you can make. So, the isotope variation. Now, here look at the complex. This is a complex of rhodium pyridine thrice. So, the previous one is the previous example was the zinc pyridyl twice and Cl2, where the zinc is used with the 64 and other one is the zinc with the 68 isotope. Now, the left side, the infrared spectrum corresponding to the rhodium pyridyl thrice Cl3. So, what do we know from coordination chemistry of this? The 3 are the one ligand, 3 are the other ligands. This is what gives the 2 isomers, which is called the facial isomer and the mer isomer, meridional isomer. So, the symmetries are obviously different. The facial isomer has more symmetry because the triangular kind of a C3 thing, and the meridional has lower symmetry of that. So, what you will expect? So, for the thing, A is the spectrum of the facial and the B is the spectrum of the meridional. In the facial spectrum, you see 2 bands here and 2 bands here. In the meridional part of the thing, 3 bands here and 3 bands here. So, you are seeing the lower the symmetry, the greater the number of bands, and the higher the symmetry, the number of bands are less, and that is what you are basically finding. So, which means even the isomer, earlier what we have seen is an isotope effect, here we are seeing isomer effect. So, this isomer effect is same as symmetry effect. So, because the symmetry is changing. Okay. So, you can use in various ways the term. So, therefore, do not be confused, and then all these you should be very clear about it. It is one and the same. So, you are talking about the isomer effect because the symmetries will differ. Isotope effect, mass will differ. So, I hope that is clear. Let us go to another example. Particularly, we will see examples of the bioorganic side in the enzymes. We will look at there are variety of enzyme examples are known, but we will take for the iron one with the hemoglobin with the CO and the O2. Let us look at this particular slide. This particular slide of the hemoglobin where CO is bound, carbon monoxide is bound, but 2 situations. The situation of the acidic, situations are the neutral. So, this is more like a basic as compared to the acidic. So, in the neutral, this imidazole is not protonated, but in the acidic, the imidazole is protonated, and this imidazole is called the distal, and this imidazole is called the proximal. And this is well known if you have studied the hemoglobin things, which I cannot go into more details of this. Now, structurally there is a difference. How would you identify that from vibrational spectrum? What will happen here? So, if you see here, this is the positive center, and this becomes straight, and no influence of this on the pi star orbitals of this. But if you look at here, there is influence of this nitrogen pi electrons onto the pi star of the carbon monoxide. So, what will happen? The nitrogen electrons, pi electrons of this is influencing the pi star orbital. So, therefore, what will happen? Whenever you bring the electron density into the pi star, what will happen? The bond order goes down. Therefore, the force constant will be reduced or the bond order is reduced. Therefore, this frequency will be lowered and this becomes stronger, and of course, vice versa here. So, this is stronger and this is weaker. Now, if you look at the data that you have already measured in the acidic condition, it is 1957, and in the basic the neutral condition 1948, almost 10 wave numbers difference, 9 wave numbers, that is okay, approximately 10 wave numbers difference, and lower. Okay. So, why is it lower? That means your C triple bond C is getting affected by the pi electrons of the pyridyl moiety or imidazole moiety, and thereby your bond order is reduced or force constant is reduced, and that is what. And accordingly, the iron nitrogen bond should be strengthened. Now, you look at this 488 507, 12 plus 7, 19 wave numbers difference, quite a lot. So 19 wave numbers difference and an increase. So CO is decreased, N is increased. That means perfectly in line with the bonding data or bonding interpretation. Here this is more, so this will be weaker, and that is what you will find. Okay. So there will be weaker and this is stronger, and this is stronger, this is weaker. Very well. Now that is one story. Another thing, if you look at the different myoglobins which are carbon monoxide bound myoglobins from different sources, you may find 2, you may find 3, you may find 1 carbonyl band. For example, here sperm whale myoglobin shows the 3 of them. That means you in the myoglobin species of the bound to CO, there are 3 kinds of interactions of the bonded one, which is a higher frequency, somewhat lower, and much lower, either in solution or in solid state. And this means that there are 3 different kinds of environments with respect to CO binding. Okay. If you look at the human, the hemoglobin CO, there are 2, because you have distinctly the alpha, the region, and the beta region, and they have the different surroundings, but due to various effects that you will see that the alpha and beta are showing, the one is 1950, others is 1930, something like 20 wave number difference in that. Okay. And case the some other example where you have seen here, and these are in this case of human, these 2 are overlapped. In the case of rabbit, these 2 are different, and you will find these 2 frequencies of this. So, and also it is found in this case of the rabbit case, this intensity is much smaller than this, and this all will tell you about the secondary structural interactions that you have between the secondary structural protein with that of the CO, and that is what he explains. So the distal, that this is happening in this particular case is because the distal histidine acts like a nucleophile more in case of the CO for the alpha substitute end, but not for the CO of the beta region of that in case of the rabbit, and that is why. And in case of human, why they are same? Because the influence of the distal imidazole is more or less same with both the cases, whether it is the alpha region or is a beta region. That is why you get same frequency, which is 1951. But whereas rabbit case 1951 and 1928, and that means in case of the alpha, there is a strong influence of this particular moiety of the imidazole nitrogen acting like a nucleophile, but not so much so with the case of the beta unit. So little influences in the structural features, secondary structural features of proteins can also be probed by infrared spectroscopy. That is what is the outcome of this. Okay, we looked at the CO. Let us look at the O2, hemoglobin with O2. Of course, that is what is more popular. So this FeO2, this is done. You can have O2 with both the oxygen being 16, one spectrum. 16, 18 is also available, that isotope. You can use the IR spectrum. Totally 18 isotope, you can use the IR spectrum, and this is the difference is seen here. So that means you can look at the O2 stretching frequencies, FeO2 stretching frequencies, but what are shown here is the FeO stretchings. So FeO stretching in the hemoglobin was first observed at 567 centimeter inverse, and this is because of the end-on geometry. So the ion with that, this is the end-on, no contact with this, that is what is called the end-on. Only one single contact with the O2 is called the end-on. So any other things is not an end-on kind of a binding. So that is where you have. And now if you take this with the O16, O18, in the other case, in one case O16, O16, the other case O16, O18, and other case O18, O16. So these 2 obviously will show the same, though their bindings are different. They will not show the same. In this case it is with this, in this case it is with this, in this case it is with this. Okay. So the frequencies will differ, because here 16 nucleus is there, 16 mass is there, 18 mass is there. Okay, 16, 18, 18, 16, and one more you have is O18 and O18. So these 2 will be the same, these 2 will be the same, but this frequency will be different from that of that. So that is where the gimmick that you play with the isotope, and that's what is shown here, explained, and these are all corresponding to the end-on kind of thing. So 16, 18, 18, 16, all of these. You can also look at this the OO, the bending. So this bending part of that will also get influenced by whether you have a 16, 16, 16, 18, 18, 16 and 18, 18, and that comes around 425, and that is not you find from the infrared, but you rather find from the Raman. So Raman spectrum gives that one in this. So if you take the difference between these spectra that you will find between the A and the C, which is completely 16 and completely 18 infrared spectrum, what you are finding, this last one is the difference one. So here this band in the upper side, this band in the lower side. That means you have the more intensity on this side, more intensity on the other side. Here again the same kind of a thing. So that is where the difference. That's what exactly you expect, because in one case you have 16, other case you have 18. And this clearly talks about the end-on mode of this one. If it is not the end-on, this difference would have changed. If it is both the oxygens are. So that is how the infrared spectra helped in proving that the O2 binds only in this way end-on, but not by the side-on. Okay, so therefore the observed splitting was attributed to the Fermi resonance between this one, etc. So you don't need to worry about all of those aspects of it. Okay, so we looked at the CO binding, we looked at the O2 binding. We need to look at the NO binding. It is also important in bioinorganic chemistry. The NO transport in many of these systems is important in the blood, and the iron containing proteins like myoglobin and hemoglobin. Okay, so if you see the geometry, this one is of course important, Fe3NO, and delta, that is the bending. So stretching vibration and the bending vibrations are these observed. These are observed at 595, 573 centimeter inverse, and these are. Now if you look at the metal bound NO stretching frequencies, the manganese 627, the iron 595, the cobalt 576, the iron 2, of course you can keep this aside, but if you compare, so manganese, iron, cobalt, all of these. So this is expected, the bonding order of this. We have seen earlier for the bonding order of the metal nitrogen coming from the ethylene diamine. Here we are looking at the nitric oxide complexes. So the resonance Raman spectra of NO adducts of manganese 2 plus complexes of unprotected and strapped porphyrins have been compared, and then that is how these things have been found. So all of these have been proven based on particularly of the Raman spectroscopy. So this vibrational spectroscopy is a very useful technique in all of these. Now let us look at a few Raman examples with this Raman spectrum of the PCl3. If you look at the PCl3 and if you draw the vibrations, PCl3 4 atoms, 3 into 412 minus 6, that is the kind of vibrations of which the Raman, the active ones are these 4, these ones, the symmetric, the nu, and asymmetric are this nu, and the bending, symmetric bending. So these are the 4 which are Raman active. We are looking at only the Raman active bands in this. And if you look at the spectrum, of course by looking at, you will know the directions of the vibrations, and thereby you can find out the net dipole moments, etc., how they are working in these things. There are some things written in the bracket A and E, you don't need to worry, that comes from the group theory which we are not taught to you. And this is even the labeling of nu 1, nu 2, nu 3, nu 4 are coming from the group theory. But in any case, these are also being labeled as nu S, delta S. Delta is for the bending, nu is for the stretching. So S is for the symmetric, A is for the asymmetric. Now you can see there the things, this is in the Stokes region and this is anti-Stokes region. You don't need to see both the regions, you can see it only one, enough. So with respect to the nu 0, this is the shift is happening, this is the shift happening with this. So asymmetric delta, symmetric delta, and then here the symmetric stretch and asymmetric stretch coming over the same and almost close by, but you can see some kind of a little doublet kind of thing. So you can see all these 4 vibrations of the PCl3 active in Raman are also seen here. Okay, so that you can see this is the Stokes region of the Raman. This is the anti-Stokes region of the Raman, and I have already explained to you the anti-Stokes region is much more weaker than the Stokes, and because that absorbance ratio will be 10 power minus 11, whereas for the Stokes is 10 power minus 8. So you need to use more and more intense light to get these things. So if you use just simple, you may not be able to find all that. Okay, another example here we are looking at Raman spectra of some inorganic compounds, just like we have seen the infrared spectra of that. You can also look at that. And this is the M is copper, a zinc, and as a nickel, and this is the nitrile compounds, the nitrile connected compounds. So in other words, nitrile linear bridge compounds. So linear bridge these are all of important in various catalysis, polymerization, etc. This is not a part of that. And then 3 of these ligands bound to the nitrogen. One set. The other set is the copper, zinc with the nickel is the cadmium. So cadmium with the nickel. So obviously with the copper, zinc to the cadmium, the difference is the heaviness. So therefore you can also see that. Of course the structure is different, but still if you look at the CUN stretching vibrations, CUN versus CDN or ZNN versus CDN, obviously there will be a huge difference. Therefore you can use that as the criteria to look at. For example, all these metal nitrogens will come somewhere 400-500 and below. So this is the region. You can see that this cadmium case versus the zinc case versus the copper. So this is the copper nickel, this is the zinc nickel, this is the cadmium nickel. So but you can see the more or less the bindings are there, except for one of these imidazole moiety you have a nitrile. This is extended network of that. So by looking at this main region of the metal nitrogen region, you can definitely work out whether it is coming from this cadmium nickel polymer or it is coming from the copper nickel or zinc nickel polymer very easily. And these are the spectra shown. Particularly you need to see below 600 in this particular region of that. But otherwise these are all with very close in terms of the binding things. So overall comparison of the spectrum of the Raman peaks of the copper nickel of this polymer, zinc nickel of this polymer, and cadmium nickel of this polymer, you can assign that the variations. You can also see some variations coming in this as well. So which is coming from the nitrile region and the other NH regions, etc., and CH regions as well. So you can make. Okay. So let us look at some additional example of the Raman. For example, when used for nanoparticle, I have explained to you some examples based on the infrared, but based on the Raman, you can see that zinc oxide nanoparticle. So these basically this is done Raman, because Raman case you need to excite at a particular wavelength, and then you look at this the virtual state back to the ground state coming in. So that is where you look at, and that is where you pump in. So therefore more and more intensity can come. That is what is called the resonance Raman. So under that certain vibrations will get more intense than the other. So the weak peak located at the 307 and 603, these are attributed, that is these weak ones are from the optical bands. So this the phonon modes, and which are coming from the silicon. So that means here the substrate is used silicon, and that you have coated the zinc oxide nanoparticle. So therefore that also comes. So you can see that the silicon signatures are this. Then the 432, and this is basically a second order Raman of this, and we don't need to know these modes, etc. A typical characteristic of the hexagonal woodsite. This band comes for the hexagonal structure of the zinc oxide woodsite, because there are a variety of zinc oxide structures are there. There are 2 more modes are there, 494 and 707, and these are coming from the zinc oxide Raman spectrum, which are coming from the surface attached. So you have a silica, and then you have a zinc oxide nanoparticle. These are surface attached onto the things. So these are surface optical phonon modes. So nanoparticles, composites also you can study. Yes, here we have a composite. So nano composite. So this nanocomposite is silver on the CNT, that is carbon nanotube, again a hybrid. So you can just look at the pristine carbon nanotube the Raman, and the modified carbon nanotube, and the silver where you have the silver attached with the carbon nanotube. So you can, by looking at these main bands of the D and G and the G prime, their intensity ratios, their positions, the structure. So there is a little structural variation as compared to this, and this like double thing, and the intensity variations of this. So you can talk about the presence of this modification on the CNT and the binding of the silver to the modified one. Okay, both of these. So CNTs can be slightly modified organically and then connected to the, because the functional groups will come and then connect to the silver nanoparticle, and these details of the frequencies are given over here. So relative intensity of the DNG bands, as well as the nature structure of each of this band, the side ones, internal ratio like IGO by IG, in case of DIGO by ID, these bands. So these will help in explaining the crystallinity, also degree of crystallinity, everything can be talked about in the nanocomposite formation. So you can evaluate the nanocomposite structural features, you can evaluate the characterization, and then you can talk about how this would help for the catalytic or whatever the property that you are choosing for. Okay, Raman spectrum can also be used for a mixture of the gaseous molecules. There is an exhaust fume chem. It has H2, it has C7, H8, C6, H6, etc. You can get a lot of, and then from intensity you can talk about the composition. Okay, so this is an exhaust coming from an engine, second cycle. This is what I have showed you. Try to sit, and a lot of such data can be obtained from Nakamoto book also, or from other papers, and you can try to compare by changing the metal ion, by changing the side anionic part, by changing the binding group, whether it's nitrogen or oxygen, all of these make the comparisons. I would like to tell you that it's a very important thing. Last but not the least is that always for every topic we are looking at how to gain better knowledge. We can only gain knowledge better by doing practicing. So knowledge enhancement by extended practice. So I've already demonstrated all of these in my lectures. This is the fourth one on this vibrational spectroscopy, and if you look into that, covered every aspect that is required for inorganic characterizations, comparisons, quantitative things, etc. Let us look at this. What I am trying to make, don't restrict to these queries only, but these queries are very important. So vibrational frequencies are influenced by the presence of the isotope. I have already demonstrated. What is that? Why is that? How is that? You should probe that. I have explained all that, but I wanted you to probe and come out. So then you take a couple of examples from the internet space and support your conclusion. What is it? Why is it? How is it? Okay. Now by taking the ion spectral data of a series of metal complexes through down the group, like taking from 3D, 4D, 5D, etc. Metal L, you can take complexes nitrogen bound, or you can take complexes oxygen, you can take complexes of sulfur or any other, but the same series you take that, and in all the cases for 3D, 4D, the vibrational frequencies decrease, that we know we have shown, and also make a plot how this decrease. Is it linear? Is it non-linear? If it is non-linear, how exactly? How the atomic mass. Now look at this formula which I gave and try to fit with that. Okay, and the comment on the graph. You can comment on the graph only when you do the calculation of that simple calculation. Whatever is the bond, metal ion mass and the L mass, 1 by metal ion mass, 1 by that will give you, and then you can explain the ratio, how it's changing from 3D metal to the 4D metal to the 5D metal. Not for the nitrogen to oxygen to sulfur, nitrogen oxygen then sulfur, yes, can also be. Between nitrogen and oxygen you may not find too much difference. The difference will be because of the more of a bond order force constant rather than of a mass. But between nitrogen and sulfur, oxygen, sulfur, it is because of the mass. So you can test your things by sitting at your home from this data. So, I also urge you to go to the using the literature data on FTIR of inorganic compounds as catalysts, a lot of things. Please practice the identification and characterization of these before and after the catalysis. They say that the catalyst is intact based on the FTIR. How is it intact? Please address that by looking at a few examples. Another the practice session that I wanted you to do with the same type of ligands, choose IR spectral data for 3 different complexes wherein the geometry of the metal ion changes from tetrahedral to octahedral to square planar, and then use the preferably same metal ion so that you can look at it. So, compare the data and analyze the results, how the change in the geometry affects the vibrational frequency. Comment on the trend and its origin. Of course, if you are interested and if you are familiar with that symmetry also, you can use that, but not required because I have not covered in this particular course the symmetry aspects, no group theory of this. Okay, so that brings to an end of the vibrational spectroscopy applications towards the inorganic complexes. I will come with another edition on this of the inorganic complexes in the next lecture. Thank you very much.